Hello, everyone. Let's do question 6 from the January 2021 CSEC Physics Paper 2. So part A reads that figure 7 shows us the experimental arrangement of the apparatus used to carry out the Rutherford's alpha particle scattering experiment to identify the structure of the atom. A collimated beam of alpha particles from a radioactive source was fired at a thin piece of gold foil, and the angle of deviation of the alpha particles were then observed, right? And so here we can see the figure here, figure 7, which is just a setup for Rutherford's alpha particle scattering experiment. So we have a radioactive source here of alpha particles. We have that, and that's being fired at this thin piece of gold foil, and then they measure the angle of deviation right afterwards to see what happened to the alpha particles that were shot at the gold foil. Okay, so here you see we have some deflected particles here, we have some scattered particles here, and they say that most of the particles are undeflected, right? So let's scroll down and see what part I is asking. Part I says, write the names of the 2 scientists who assisted Rutherford in performing this experiment, right? So based on our knowledge of this Rutherford's alpha particle scattering experiment, we might remember that the 2 scientists who helped him were Hans Geiger and Ernest Marsden, right? They were working in Rutherford's lab at the time, and they helped with this experiment. So those are Hans Geiger and Ernest Marsden. So you say these two guys, we get our 2 marks, okay? So moving down to part 2, right? Explain why the experiment was carried out in an evacuated chamber. So when they're doing this experiment here, this is all contained within what's known as an evacuated chamber. And the reason for that is because the alpha particles, so these alpha particles that are coming from the source, they are stopped by just a few centimeters of air, right? So you want it to be such that it's completely evacuated. There are no air particles there to interfere with the movement of those alpha particles that you're firing at the thin gold foil, okay? So we use an evacuated chamber for that because a property of alpha particles is that they're stopped by a few centimeters of air, okay? So that's the purpose of that. For 2 marks, we are good. Moving along to part B of this question. Part B says to state the conclusions that were deduced from each of the following observations made from the alpha particle scattering experiment. So they wrote down some observations and they were able to deduce a few things based on those observations. So the observations that were made in part I, they're saying the first one was that most of the alpha particles passed through the gold foil undeviated, right? So most of the alpha particles passed through the gold foil undeviated, right? And the conclusion from that was that most of the atom is made up of empty space, right? So empty space, that's why the alpha particle just go through without obstruction, any obstruction really, because it's mostly empty space. So let's see, for part 2, a few alpha particles were deflected from their path, but continued through the gold foil. So when they saw this observation, now what they deduced from that, what they concluded, right, was that the nucleus is very dense and consists of positive charge, which repel the alpha particles. So you had these few alpha particles that were deflected from their path, but they continued through the gold foil. So that deflection came as a result of repulsion, right, from the positively charged nucleus. So that was the conclusion that Rutherford made in this particular instant. And then for part 3, another observation that they made was that a smaller number of alpha particles rebounded, right? So you had a certain amount of them that just when they hit the gold foil, they just kind of rebounded. They bounced right back, right? So they like just bounce back in this direction, in the direction that they're coming from, right? And a smaller amount of them did that. And the deduction or the conclusion that they made was that the repulsive forces, right, those increased as a small number of alpha particles came close to the nucleus. So you have a small number of those alpha particles coming close to the nucleus of that atom. And so those alpha particles, when they collide then with the nucleus where we have that positively charged protons, they completely rebounded, right? So because of that magnified repulsion. So that's what the deduction from this observation would be, okay? Would or and was in this case. So all of that for 1 mark, we are good to go. All right. So moving down to part C now, we have to put everything together, and they're asking us now to describe the Rutherford model of the atom based on the conclusions of the experiment stated above. So we had 3 conclusions here that we came out with, and when we put those 3 together, we get the description of the Rutherford model of the atom, which is that most of the atom is made up of empty space, and that it contains a nucleus of very concentrated positive charge, right? So that's what we can say. We can come up with that description of the Rutherford model based on those conclusions in part B. And so if I were to do a quick sketch of what it looks like, or what Rutherford had came up with, right, was that you have this in the central part of the atom, you have a concentrated positive nucleus. And then around that, of course, you'd have the electrons that are scattered in the region that's mostly empty space, okay? So for all of this, we'll get our 2 marks. The model is that the nucleus is positively charged, very concentrated, and the rest of it is mostly empty space. And in those empty spaces, we can find our electrons, okay? So all of that for 2 marks, and we are good. Moving right along to part D of this question. And part D states that there's energy that is produced within stars by the process of fusion, right? A fusion process where alpha particles help convert beryllium into carbon according to the equation below. So we have our helium nuclei, which is our alpha particle, which represents our alpha particle. Then we have a beryllium atom rather here. And then when we fuse these 2 together, right, what happens is that there's like a neutron that's liberated and carbon as well, right? So that's how this whole thing works. So in the equation above, which symbol is used to represent the alpha particle? As we said, we represent an alpha particle as a helium nuclei. So this helium symbol, right, is what represents our alpha particle. So we just write that down here. 42He represents our alpha particle. Okay? So moving down to part 2, we're given a table here, and the table shows the mass of each nuclei in the process above. So remember up here, we had our helium nuclei, we had a beryllium nuclei, we had our neutron that got liberated, and we also had our carbon nuclei. So this table is showing us the mass of all of each of these nuclei, right? So this is just the mass, and this mass, please pay attention that this mass is actually given in atomic mass units. So that's what this U is. It's just atomic mass units. It's not an SI unit, right? So they're asking us now to calculate the loss in mass, delta M, in kilograms, right? So we have to put that in an SI unit now due to the reaction, right? And so whenever we see that we're given mass in just atomic mass units, we're going to always need to apply this conversion factor here, which says that 1 atomic mass unit, so one of these weighs 1.6 or is equivalent to 1.66 times 10 to the negative 27 kilograms, right? So they're asked us to calculate the loss in mass, which is delta M. So the first thing that we're going to do is we're just going to rewrite our nuclear equation. So that's what I did here, right? So this is my nuclear equation here I've written in this line here. And so we know that the fusion, right, the way that the fusion works is that we have this alpha particle combined with a beryllium nuclei to then liberate a neutron and this carbon nuclei, right? But in that process, of course, they told us in the question that there's some energy, right, that's liberated as well. And so we know from Einstein's equation, which relates energy to mass differences or a mass defect, we know that this energy that we see comes about due to the delta M or the change in M, right? And that's what they're asking us to calculate here, is that delta M, right? So we need to know which part of this equation actually is delta M, would represent delta M, so that we can actually calculate it, right? And so that's why one of the first thing I did was to rewrite this equation, and I added in my delta M here to show that that's where delta M would be manifested, okay? So then all I do from there now is I'm gonna take the atomic mass units for helium that they gave me from the table, which is this, 4.00260 units. I'm going to convert that to kilogram first and foremost. So I do that for helium. I do the same thing for the beryllium. I do the same thing for my neutron, and I do the same thing for my carbon. Again, this first step is converting. So let's write that here. What that first step is, we are converting our atomic mass units to kilograms, right? For that very first step. And so to do that, we just multiplied by the 1.66 times 10 to the negative 27. We multiplied the given mass units, right, for the respective nuclei by that. And then so we come out with our kilogram value. So all these values here now are in our SI unit of kilogram, right? They're all in kilogram, and they asked us for the delta M in kilogram. So it was important for us to do that conversion up front, right? So we did that conversion now. We have all our masses of the nuclei in kilogram. And so at this point now, all we have to do is rearrange. So bring everything to one side and leaving M on its own, because M is what we want. Delta M is what we actually want. And so what I ended up doing then was subtracting all of this from all of this. And so that number came out to be our delta M, and that delta M ended up being 1.0043 times 10 to the negative 29 kilograms. Okay, so that's our delta M. 1.0043 times 10 to the negative 29 kilograms. Okay? All right. So moving down to the next part, they're asking us to calculate the energy equivalence of the mass that we calculated in D part I, right? So we calculated this delta M, and remember earlier, I said that based on Einstein's equation, we know that there's an equivalence between the mass defect or the delta M and the energy that's liberated, okay? And so we can use Einstein's equation, which says that delta E is equal to delta M C squared, right? And we had just calculated our delta M from here, right? We knew it was 1.0043 times 10 to the negative 29. And so when we came down here, all we had to do was just plug in that delta M here, and then plug in our C, which is the speed of light, and square that. So it's C squared. So we're going to square our C term, and then just multiply everything together, and we'll come out with the energy equivalence of that mass that we calculated above, right? So delta E, in this case, ended up being 9.0387 times 10 to the negative 13 joules. Remember our units. Units are important. So it's 9.0387 times 10 to the negative 13 joules, right? And that's worth 3 marks, and that's the end of this question, right? So again, if there's anything that's not clear from this question, how we arrived at the particular answer, definitely drop that in the comment section below. And if this was helpful for you as well, drop that in the comment section. Be sure to like and subscribe to the channel, and I'll see you in the next video.